The topic for the lecture is classical logic. So previously, we learned that we can obtain classical logic as an extension of constructive logic. We have this constructive logic, and we can add a new inference rule called law of excluded middle, which reads A disjunction negation A is true. So this inference rule is called law of excluded middle. So it says that for every proposition A, you have either for every proposition A, you have either A true or negation A true. You may not have a proof of A true or negation A true. It doesn't matter because what we know is one of these two judgments must be true. So that's the law of excluded middle. So this is an easy way to obtain classical logic. So this is now classical logic. And there is another way to obtain classical logic as an extension of a constructive logic. And this time we have this constructive logic. And this time we add this rule called double negation elimination, which reads double negation A implies A true. So for every proposition A, we have this one as an axiom. So this rule is called double negation elimination, the law of a double negation elimination rule. Because this is a double negation, we have not just one negation, but we have a double negation. And double negation is automatically eliminated in classical logic. So this is called, this inference rule basically states the law of a double negation elimination. And the interpretation of this double negation elimination is if A cannot, we read the first negation as cannot. If A cannot be false, we read the second negation as false. Then A is true. There are only two choices, either A is true or A is false. So if A cannot be false, then it must be true. That's what this inference rule, double negation elimination, states. And if we think about this is precisely the principle behind proof by contradiction, which should be familiar from those proofs back in high school math. And it's easy to see because this double negation A can be expanded as negation A implies bottom, according to our notation definition. Recall that we defined negation A as A implies bottom. So by expanding the first negation, we have double negation A as negation implies bottom. Now, this one says double negation implies bottom, and it means that in order to prove A true, so in order to prove A is true, it suffices to prove double negation A is true. But double negation A means negation A leads to bottom. So we can read this formula as assume negation A, or A is false. Then we obtain bottom or contradiction. So we start with the assumption that A is false, and then we somehow generate contradiction. Then, thanks to this law of double negation elimination, we can deduce A is true. So that's precisely what happens when you employ the technique of proof by contradiction. To prove A, in order to prove A, assume A is false, and then somehow show that everything is self-contradictory, show the contradiction. So this is basically proof by contradiction. So this is the first way of obtaining classical logic as an extension of constructive logic. And this is the second way. You add this law of double negation elimination. There's yet another way to derive classical logic as an extension of constructive logic. So that is Peirce's law. So we have this constructive logic. And now we are going to add a new rule called Peirce. So it's not P-I-E-R-C-E, it's actually P-E-I-R-C-E. And this Peirce's law says we have A implies B implies A implies A is true for every proposition A and B. So that's another way to obtain classical logic as an extension of constructive logic. So it takes a bit of thinking to interpret this Peirce's law. So let's go over the meaning of this Peirce's law. So we have A implies B implies A implies A true. So the story goes as follows. I would like to prove A is true. So in order to prove A is true, in the presence of this Peirce's law, it suffices to show this formula is true because we have this Peirce's law. So in order to prove A true, we can instead prove A implies B implies A is true. So the problem has been rephrased. We started with the goal of proving A true. Now the goal is to prove this judgment. But the interpretation of this judgment is assume A implies a bottom true for any proposition B and then prove A true. So we started with the goal of proving A true. Now we find ourselves making assumption A implies B true for any proposition B, while the goal is the same. So to say again, we started with the goal of proving A true. So this is the original goal. But by exploiting this Peirce's law, now we have the same goal as before, that is proving A true. But now we may make assumptions. We may introduce this assumption for any proposition B for free. So in other words, this assumption is given for free. Now, because we have these new assumptions, the problem has been somehow simplified. We are trying to prove the same judgment by exploiting new assumptions. Now, what does this mean? Here, we may assume A implies B is true for any proposition B. In particular, for example, we may choose B as bottom. So let's consider the case of setting B to bottom. Then what happens? Assume A implies bottom true, and then prove A true. So that is assume negation A true, and then we needed to show A is true. But if you manage to prove A true in the presence of this assumption negation A true, you essentially generate the bottom, because this A true and negation A true contradict each other. So the story can be summarized as you assume negation A true, and then you prove bottom true. Then you eventually you manage to prove the original goal, namely A is true. But there's some common element between this Peirce law and this double negation elimination. So intuitively, if you can make an assumption A implies B true for any proposition B, basically you are saying that A is false, negation A is true. So that's the idea. So now we have learned that there are three ways to derive classical logic from constructive logic by adding just a single additional inference rule. For example, this Peirce law, or double negation elimination, or this law of excluded middle. So this is a good working definition. This could be accepted as a proof of theory for classical logic, but this is actually bad. And the reason is, in the case of a law of excluded middle, we have A disjunction negation A true. This is law of excluded middle. And double negation elimination reads double negation A leads to A true. And Peirce law reads A implies B implies A implies A is true. And these inference rules are bad because they destroy orthogonality of the system. The previous constructive logic, this constructive logic, is orthogonal in the sense that every connective is defined independently of any other connective. In other words, all the logical connectives, implication, conjunction, disjunction, these logical connectives are defined independently of each other, so they are orthogonal. So, for example, figuratively speaking, implication goes this way, but conjunction goes this way, so they are orthogonal. So they don't meet, they don't depend on each other. But once you throw in one of these rules, the orthogonality of the system is destroyed. So for example, in the case of a law of excluded middle, now the meaning of disjunction depends on the meaning of negation and vice versa. And if you expand negation A into A implies bottom, now you have three logical connectives: disjunction, implication, and bottom, and they are all interconnected with each other. Now you cannot explain the meaning of, for example, implication in isolation without referring to other logical connectives. In order to explain the meaning of implication, now you have to talk about this disjunction as well. So the orthogonality is destroyed. And similarly, in the case of a double negation elimination, we have this negation and implication. And negation involves, if you expand the negation A into A implies a bottom, now the meaning of a bottom and the meaning of implication, they are uh, interdependent, interconnected with each other. But I guess the best example is this Peirce law, because this rule appears to preserve orthogonality, because now you have only one kind of logical connective, namely implication. So it appears like this Peirce law preserves orthogonality, but in reality, it actually destroys orthogonality, precisely for the same reason as before. So this time, the meaning of this implication, this logical connective implication, depends on the meaning of this logical connective implication. In other words, in order to explain the meaning of this implication, you have to presuppose the notion of implication. So it's like inductive definitions or recursive definition. In order to explain the meaning of recursive function f, you have to assume, let's say you have recursive function f. In order to explain the meaning of this recursive function f, you have to look at its body, function body. This is function body. But inside the function body, you have a recursive reference to the very function being defined. So we have a similar situation here. You cannot explain this meaning without relying on the meaning of the same logic connective. So in this regard, we can say that this Peirce law also destroys orthogonality. So our first attempt to derive classical logic as an extension of constructive logic is actually bad because of the orthogonality being destroyed. So let's take a different approach. So we'd like to formulate classical logic using two kinds of judgments. First, two kinds of judgments. And also the idea of proof by contradiction. So if you recall any proof based on classical logic, then we notice that the heart of any proof based on classical logic is actually proof by contradiction. You always try to generate contradiction after making an assumption that the conclusion is false. That's the typical pattern of classical logic. So the heart of the proof in classical logic is proof by contradiction. So we have to use this idea some way, in one way or another. And we'd like to introduce two kinds of judgment, namely truth judgment and false judgment. Uh, so here's the concrete ideas. First, in order to prove C true, we assume C false. So now we see the use of a new form of judgment, is a forced judgment, and then prove contradiction. So that's the idea behind this proof by contradiction. Now we have to also explain when we can generate the contradiction. So we obtain contradiction whenever we have both A true and A false. It doesn't matter what kind of proposition A we have. Any proposition is fine. Whenever you have both A true and A false, the situation is self-contradictory and we have this contradiction. So the first idea, this one, basically says we want to use proof by contradiction, the technique of proof by contradiction. To prove C true, assume C false, and then somehow show contradiction. And the second part states how we can generate the contradiction. And the idea is whenever we have A true and A false as an assumption or as conclusion, whenever you have A true and A false, we show this contradiction. So that's the essence of this new formulation of a classical logic. And notice that we have now two kinds of judgment: truth judgment and false judgment. And it requires actually quite a bit of thinking to figure out the right form of hypothetical judgment, even with all these ideas. And the hypothetical judgment that we are going to use looks like gamma, delta, turnstile, C true, where gamma is basically assumption, a collection of assumptions of truth judgment, whereas delta is assumptions of false judgment. So notice that we only deduce truth judgment and we never deduce false judgment directly. We only use false judgment as assumptions. So these are hypotheses. These are basically hypotheses, right? So we can make assumptions of a truth judgment, as in delta, and we can also make a false judgment as assumptions of false judgment using this delta, this context delta. And we could also use the subscript k to denote classical logic. So this is the new form of hypothetical judgment that we are going to use to formulate classical logic. So the key point here is we can make assumptions of a truth judgment. These guys are all truth judgment as assumptions. And we can also make assumptions of a false judgment. But we only deduce truth judgment in the conclusion. So that's the hypothetical judgment that we are going to use. Now, let's try to formulate the inference rules based on this new form of hypothetical judgment. First, we can easily extend in a straightforward way all the existing inference rules from constructive logic. So for example, in constructive logic, we have this implication introduction rule. So assume A true and then deduce B true. And we can and this is classical logic. And we can derive a corresponding inference rule in classical logic simply by adding new context to delta. So remember that without this delta fragment, the judgment degenerates to the familiar form gamma turnstile C true that is used in constructive logic. So what's new in classical logic is we add another context that contains the set of forced judgments as assumptions. And these forced judgments do not interact with existing inference rules. So you can simply add delta. So for example, you add delta here and add delta in the premise as well. And now you have implication introduction rule in classical logic. So in this way, you can revisit every inference rule in constructive logic and then derive a corresponding inference rule in classical logic. Now you have to add some new rules, otherwise this classical logic is essentially, this system is no different from the previous constructive logic. Now let's add two inference rules here. Two inference rules. And these two inference rules capture the idea explained here. So we needed to introduce a new inference rule that allowed us to make an assumption, forced assumptions, when the goal is to prove C true. So in other words, we have to translate this idea somehow into a new inference rule. And we also have to translate this idea into another inference rule. So the second idea is basically whenever you have both A true and A false, you can generate a contradiction. So let's try to translate these two statements into their corresponding inference rules. So the first is to prove some stuff to truth judgment, you may assume the corresponding forced judgment. So the first inference rule is written like, suppose that we have these two contexts in classical logic, and currently we'd like to prove A true. In classical logic, when the goal is to prove A true, you may assume A is false. So the delta context is now extended with new hypothesis, new assumption. And then you prove the same judgment. So we have seen this pattern before in the double negation elimination, also in the Peirce law. When the goal is to prove A true, you are free, you are permitted to introduce new hypothesis, new assumption of A false without changing the goal. And if you manage to prove A true under this extended assumption, then basically you have contradiction because you assume A false and you prove A true. Combining them together, you show bottom is true. So essentially, this premise says that we have generated a contradiction. And we decide to we call this rule as contradiction up arrow, where this up arrow indicates that this rule is best read upward in the bottom up way. So start with this start with the conclusion and then try to read the judgment in the premise, which simply says, I'd like to prove A true, then just introduce A false as a new assumption. So this is the contradiction of error rule. And this rule corresponds to the first statement, this one. Now we have to translate the second part into another inference rule. This one says, whenever you have both A true and A false, then you have a contradiction. So assume that you have both A true, so you have shown A true, and you have also A false as an assumption. Then you have just generated the contradiction. Then, because this set of assumptions, this context can generate A true, which contradicts one of the assumptions, A false. So it is contradiction. So now whenever you have the same context, gamma, delta, A false, you can always show that contradiction can be generated. Therefore, you can prove any judgment. And this time, this rule is best read in a top-down way. So let's call this rule contra down arrow. This is down arrow because you'd like it to start with the judgment in the assumption, in the premise. So by adding these two inference rules, So in order to formulate the proof theory for classical logic, we first extend all the inference rules from constructive logic just by adding this new context delta. And then we add two inference rules, contra up arrow rule and contra down arrow rule. Contra up rule says that when you'd like to prove A true, you are permitted to assume A is false. And the second rule, contra down rule, says whenever you have a contradiction, whenever you have both A false and A true, you have shown the contradiction, so you can prove anything for free. And notice that these two inference rules appear to play completely different roles, but they have precisely the same premise. From the same premise, you deduce different judgments. So this is how we obtain classical logic, proof theory for classical logic. And this new formulation is still orthogonal because all the inference rules derived from constructive logic preserve orthogonality. So in other words, this is orthogonal. Therefore, this fragment is also still orthogonal. And these two inference rules still preserve orthogonality simply because there is no logical connective here. Everything is explained in terms of the notion of judgment, not logical connective. So we have formulated the classical logic without destroying orthogonality.